Okay, you know those viral posts you see floating around? The ones claiming there are just 8 magical database indexes you can plug and play to fix literally any performance issue? Well, treating your database indexes like power-ups in a video game is a massive trap. And honestly, it's usually one that ends with a 3 a.m. pager alert. Welcome to this explainer. Today, we're going to completely dismantle that myth and build a real, authoritative mental model of the database index types that actually matter.
Here's how we're breaking it all down today. We'll start with the index taxonomy problem, move into the workhorse indexes, look at some highly targeted optimizations, figure out how to handle complex data, build a reliable decision framework, and finally, validate everything with hard proof. Let's get into it.
All right, part 1, the index taxonomy problem and why we really need to rethink those 8 types.
Look, that viral list of 8 indexes is a neat little memory aid, sure, but treating all of them as a single, flat menu, that's how bad architectural calls happen. The true taxonomy actually separates these ideas into 3 distinct categories. You have access methods, definition patterns, and search subsystems. B-tree, hash, bitmap, gin, and gist, those are your access methods, the actual storage families. Things like composite, covering, and partial, those are definition patterns, meaning they're ways to shape those methods. And full text, that's an entirely separate search subsystem. Separating these concepts in your head makes the whole topic so much easier to reason about.
The biggest danger of the myth is assuming you've just got 8 interchangeable magic wands at your disposal. The reality is far different. You're working with those 3 distinct categories, and they're governed by strict, engine-specific rules. You literally cannot ignore how PostgreSQL handles things differently than MySQL, SQL Server, or Oracle. If you do, you're going to make bad calls quickly. Engine portability matters, so don't assume a feature works exactly the same way across every platform.
Moving right along to section 2, the workhorse indexes. We're talking B-tree, hash, and composite.
Let's kick this off with the undisputed king of access methods, the B-tree. Think about how the standard SQL creation syntax compares directly to its internal tree branch structure. The B-tree is the default for a very good reason. It perfectly handles equality, range filtering, and sorted output across all major database engines. When your query uses a between clause, an order by, or just basic equality, the B-tree's sorted keys and lightning-fast navigation down to the leaf pages are exactly what you need.
Now, I really need you to hear this one. A hash index is not just a faster B-tree. Actually, scratch that entire idea from your mind. It is a huge, dangerous misconception. A hash index is a highly niche tool with strict engine constraints. It only supports exact equality. That means no range scans, no sorting. 0. Plus, engines heavily limit it. MySQL mainly uses them just for memory tables, and Postgres documentation clearly presents them as a specialized option. Definitely not a general recommendation.
Next up, composite indexes. They aren't some exotic new tech, they are just multi-column B-trees done thoughtfully. But the golden rule of thumb you absolutely have to memorize is this. The column order is the actual product. Rule 1. Equality columns go first. Rule 2. Range columns come next. Rule 3, sort columns go last. You can't just throw a bunch of columns together in a blender and hope the database optimizer figures it out. Because think about it, those leading columns totally dictate the index's usability. If your query maps to the leftmost prefix of the index, say querying tenant_ID, status, and created_at all together, it's the absolute best fit. But if you omit that leading column from your search, the index is effectively dead weight. Order is everything here.
All right, part 3, highly targeted optimizations, or how to really shape your indexes. This is where we shift from basic access methods to definition patterns. These are highly targeted ways to shape how an index interacts with a specific query, and it's where things get really fun. The magic here is the difference between a standard lookup path and a highly efficient index-only path. By using covering indexes with the include clause, you keep the core index narrow, but you pack in the exact payload columns your query is asking for. The database can then just return the rows directly from the index tree itself. You avoid the base table heap fetch entirely, which is a massive I/O savings right there.
Want to save a ridiculous amount of disk space and memory? Enter the partial or filtered index. This basically means indexing only a specific subset of rows selected by a predicate like status equals open. Instead of indexing millions of closed, historical orders, you're only indexing the few thousand active ones. It saves space, drastically reduces your maintenance costs, and speeds up your most frequent operational queries. It's a real game changer for OLTP workloads.
And let's clear up another major trap while we're at it.
The bitmap index myth. People constantly think these are great for general performance. The reality, they are brilliant for Oracle data warehousing with low cardinality columns. Think things like gender or active status, and heavily read-biased workloads. But because updating just one single value locks the shared key entry rather than an isolated row pointer, they are absolutely terrible for heavy write OLTP workloads. They will crush your concurrency.
Section 4. Handling complex data. Enter GIN, GIST, and full text. Let's shift gears into the wild west of complex, non-scalar data. When you get here, you hit a crucial fork in the road between GIN and GIST. GIN is an inverted index, and it's perfect for incredibly fast membership lookups, like asking, hey, is this tag somewhere in this array? GIST, on the other hand, relies on bounding boxes and signatures, making it your go-to for spatial overlap and nearest neighbor searches. Knowing which side of this fork to take is going to save you so many architectural headaches down the line.
Honestly, GIN is incredibly versatile. On one hand, it completely powers tokenized full-text search over text vectors. On the other hand, it absolutely excels at JSON-B querying, looking for specific key value pairs tucked inside a large JSON document. Because it essentially stores a key alongside a list of row identifiers, it has to be your absolute go-to for any kind of multi-valued content.
Now let's look at GIST's real superpower. Take a look at how PostGIST creates a GIST index specifically for a nearest neighbor spatial query. It acts a lot like an R tree for irregular search spaces, like geography. It's undeniably powerful, but just a heads up, as the documentation points out, GIST can actually be lossy. That means it might require secondary rechecks of the actual table rows just to ensure precision, so keep that in mind.
Part 5. The Decision Framework. Let's start putting all of this together. So, bringing all these technical threads into a single, cohesive framework, how do we actually make the right choice when the pressure is on? Well, the most important takeaway from this entire explanation is this. You have to start with the query pattern, not the index jargon. You need to analyze your actual data distribution and your most frequent queries first, long before you even think about picking a specific index tool off the shelf. Here is your rapid-fire mental checklist. Number 1. Do you need equality, range, or sort? Start with a B-tree. Number 2. Are you only querying a hot subset of rows? Grab a partial index. Number 3. Can you get away with not needing the base row at all? Slap on a covering index using the include clause. It really comes down to mapping the tool directly to the shape of the query. And all of those rules build into the ultimate synthesis, a comprehensive master flowchart that maps your query requirements directly to the optimal index design. From equality-only hash options all the way to complex spatial GIST requirements, using a framework like this replaces all the guesswork with a solid structural engineering approach to your database. Finally, Part 6. Validate with proof. Trust absolutely nothing but the execution plan.
Here is the hard truth about database administration. Your intuition is never enough. Validating your theories with explain analyze is completely non-negotiable. Running that command is what actually proves whether your brilliant new index is secretly causing unexpected heap fetches, lossy rechecks, terrible row estimates, or unnecessary sorts that are silently killing your application's performance behind the scenes.
Which leaves us with one final provocative thought. Are your current database indexes actually doing what you think they are? Now that you're armed with the true taxonomy, the rules of column ordering, and the right validation tools, go audit your own production queries right now. Thanks for hanging out with me for this explainer. I really hope this transforms the way you look at your databases. Keep learning, and I'll catch you next time.